So back to the game. There's a really cool challenge I want to look at called Thermal Controller 2. And Thermal Controller 2 is a challenge written in C++. The idea is the code is representing a barbecue smoker. There's a special binary protocol going back and forth.
It's a very advanced barbecue smoker, and it's the third barbecue smoker in the game too, right? Because there was a whole series of thermal controllers.
This particular one is written in C++. It has a stack-based buffer overflow, and let's take a look at what that vulnerability looks like. So I want to step through this code, and if we look just at the top, we're talking about this read input function. This is where the binary is taking input off of the network and actually processing it. So first we see here in line 257, there is a stack buffer declared called input chars. Obviously, stack buffer, we're going to pay attention to that.
And of course, we got 512 bytes, right, to that
512 bytes long, yeah. So take a look at this while loop. The first thing that we're going to do is we're going to read 1 byte into a character. Now, we're not reading into the stack buffer yet, but we're just taking 1 byte, and then we're comparing it to the sequence start byte that we're looking for. So that's we're looking for an A5. We compare it. If we do in fact get an A5, we go ahead and copy that character into our stack buffer, and that's important. We see position pointer being incremented there.
Yeah,
now
so this is a pretty typical kind of like network-based protocol. There's a lot of these like, you know, sentinel flags and read bytes once you see that, start, stop kind of flags, that sort of stuff. That's pretty common in
absolutely.
network protocols.
I mean, A5, 5A, that's baked into, I think, Ethernet protocol. That's a pretty common sequence. So then we actually go look for the second one, and we're checking to see if it's the 5A. Now what's interesting here is if it is not the 5A, we see this statement here, go to begin. So if we match the first byte but not the second byte, we go back up to the top of the while loop. And what you'll notice is during that sequence, we incremented this position pointer, but we never reset it. So you can keep going through this loop over and over and over again and incrementing that stack buffer by 1 character at a time. And once you do it enough, you're going to go past the 512 that are allocated, and you're going to start writing over the other important areas of the stack.
And of course, unless the compiler changes the order of those arguments, the return address is going to be the next thing you're going to overwrite.
Yes, exactly. So the other thing we can take a look at is what was the original patch supposed to look like? So every challenge binary author had to create manually a patch to their code to say, yes, technically you can patch this and it will still function as normal. And what we see here is that the patch was in fact resetting that position pointer back to 0 every time you came back to the top of the while loop.
And no, that's not the required patch. They're not required to match that exact functionality when the teams submit their replacements. But their goal is to protect the vulnerability, if there are vulnerabilities, and to keep the original functionality. So there's legitimate polls that are being sent that they have to maintain, so they can't just break it and return 0 immediately. But if they can prevent POV from successfully exploiting them, then that's sufficient as long as they're passing polls and within performance characteristics, right?
And we wanted to see what did they do. So we took a look at some of these replacements. Now, several of the teams have patched this vulnerability. This is Crispy's replacement right here. Crispy's replacement did in fact patch a vulnerability. They made themselves, they mitigated the threat from that POV. What we're looking at here is on the left, we see some disassembly from the original binary.
Yeah, and I can even see that sort of this return address that we've got right here lines up with the move over here, right? Like that would have been the same thing. We can see that's the function epilogue on the left, and then it was the function epilogue on the right, and now they've added all this additional code essentially.
Yeah, absolutely. So all this extra code is what Crispy added to protect themselves. And what we see it doing is actually checking the return address on the stack against some expected values, and which are presumably the values from the program that are valid function pointers. And we see down here that if they determine that it is not valid, they're going to terminate, called the terminate system call. If they determine that it was valid, they're going to go ahead and just return like normal.
So this is, I mean, a fairly common implementation of a return address kind of protection validation. There's a lot of different examples of this. Control flow guard is a little more advanced where you're doing a lot of pointer validation, but for just return addresses, we see a couple of different techniques kind of in the wild. Stack cookies are a classic example of this, but this one, instead of inserting a stack cookie, it looks like they're just checking that return address before they return against the sort of whitelist that they've set up.
Dynamically checking that return address. And